Ladies and gentlemen, it's a real pleasure to be here in this beautiful hall. It's not the first time I'm here. I've been here on several occasions, and our cooperation has been pretty long, although it was, yes? But, oh, thank you. Yeah. Although our cooperation started long time before this 1999, and I'm really coming over to Torino almost every year. So, ladies and gentlemen, I shall be pretty brief because it's been a long day already here. I would like to just to show you a little bit about what we have been doing, and then not speaking in terms of formulas or mathematics, but just to show a couple of examples. And although Franco Pastrona mentioned Skype, and this was really somehow started in Tallinn, in Estonia, this is information technology. I am not related to Skype, so this is a little bit different model. So, it's been recognized as an Estonian Center of Excellence in Research, so it's a local programs. And what we have now, it's several departments. It's a mechanics, applied mathematics, photoelasticity, systems biology, wave engineering, and then Department of Control Systems and Laboratory of Physical Optics from University of Tartu, which is a different town. Tartu is not so close to Tallinn. And the main themes are just listed here. So it's a main problem that we are also cooperating with Professor Pastrona. It's a complexity of nonlinear wave motion in solids, complexity of water waves, so that Tallinn is on the coast. It's a Baltic Sea, which is completely in the European Union, because the others are open. Mediterranean is also open to the other continent. And we are interested in complexity of biophysics related also to some kind of mechanical problems, if we may call it contraction of the heart cells, fractality in nature, nonlinear optics, and control of nonlinear systems. So that actually one of the mottos what we have been thinking about, that if you really split up the problems into the smallest possible components, and then we are able to solve them, and we are very, very good at it. And so that Armin Toffler said it a long time ago, that we are so good at it, solving the small problem, that we forget to put them back into the whole. And this is something that we really try to do, and in general principles, from the physical viewpoint, we mean by complexity the emergence of collective properties, where the large number of parts, whether they are constituents like in the materials, functionally graded materials, or cells that interact with each other, and not only with each other but also with the environment. And then it means that something more happens than just to sum up the single parts. So that in solids, we think that these micro interaction forces between the microstructural constituents and the internal fields are of importance. In tissues, it's intracellular processes. In soft matter, it's a turbulent mixing, where there's partly statistics and partly the deformation of material elements. And certainly there are direct problems, so that we would like to understand the process. But the interaction gives more information, and the solving of inverse problems is also very important to understand the complexities or the properties of the materials, and also for example, in photoelasticity, where the interaction is between the stress fields and light fields. So that actually the keywords are written here, the nonlinear dynamics, so that it's also something that I know that some people in this audience are related to that. Complex systems, then microstructured solitons, photoelasticity, biophysics, cell energetics, surface and extreme waves in sea. That once again, for us it's an important problem. well, mathematically it's a nonlinear differential equations we have to solve. And actually, if we put them into the basket and try to a little bit just to scatter it, then this complexity comes out. So, ladies and gentlemen, now very briefly that what the 5 groups we have got: nonlinear dynamics, wave engineering, optics, nonlinear control, and systems biology. And this is just, well, the fundamentals of nonlinear processes, methods of analysis, and control over the nonlinear processes. This means that some kind of the general attitude. And certainly there are many possible applications, whether it's a coastal engineering, which is for us important, glass industry, non-destructive testing, material science, and also medicine, like it goes with these heart cells. So a couple of examples only. That statistical topography and velocity fields means that we are able to calculate the pollution in the sea. Solitary interaction, if you look at it, it's a real interaction of solitary waves, single waves, but this is just the photon. And we are able to also to understand this mathematically, understanding that this is very typical for nonlinear processes, that 1 plus 1 is not 2. In the school mathematics, you get the minimum grade of that, but in physics, you add 1 amplitude to another amplitude, and you can get 4 out of it. It depends, actually here, it depends upon the angle of the interaction, and that is something that it is really, as you see, that this could happen in nature. So a couple of examples more about how this our Wellcome Trust fellow works with the heart cells, trying to understand, putting the physiology into the context that we shall be able also to model the contraction of single cells, so that this is really with the aid of the confocal microscopes, it's possible to carry out experiments and then go to mathematics, so that without the experiments, this mathematical modeling, it would be impossible. So once again, that's something from the nonlinear dynamics. Again, the tissue excitation, for example, this is a bifurcation diagram showing that if you have got your some kind of sequence of the excitations with a certain frequency, certain intensity, you change the frequency with a constant, and you can go through it. Is it also here? No. Well, you for example, you change. Oh, sorry. You just go through it like that, changing, for example, the frequency, and you meet this region where the Lyapunov exponent is positive, meaning that you can get some kind of chaotic regime. We are able to carry on this photoelastic tomography, which is a pretty well-developed field. Several such kind of automatic polariscopes are well distributed all over the world. The companies who are interested in the stress experiments in glass specimen, whatever they are, the glass like given here, or the building glass, which is the very important part of the contemporary structure. So this is a possibility to go through it. The water waves, it's also something that it's of our interest. You can see here the bottom panel is the Gulf of Finland. So as you can oh, sorry, it goes like that. Tallinn is one side, Helsinki is another side. And these routes are the routes for possible routes for ships. And the main problem is this: if something happens, whatever it is, the pollution comes out of the oil or something like that. The idea is to get the route that the time from this pollution to reach the coast is maximum. so that it's much easier to collect the pollution on the open sea rather than it comes to the coast. And this was actually the project which was very well accepted. Certainly the companies, it's a different story, and we can't say that it's applied or whatsoever. But it's again something that is used. By the way, that we're in this beautiful room here at Lagrange is here and there. Lagrange and trajectories are used here for this project. So and then we are working also with the short light pulses, which could be used in spectroscopy. We have several international programs. The first one, Matemis, was also here related to the Politecnico di Torino and the Università di Torino, but several others like the Marie Curie scheme, the Wellcome Trust, the Euronet complexity, futuricity, and so on. So that actually, as a result, it's just some sample of the monographs published within the last 6 years, I think so. It's a numerical simulations, applied wave mathematics on the cooperation, microstructured materials for the inverse problems, and then preventive methods for coastal protection. This is also something that's related to the Gulf of Finland. We also have these annual reports. Professor Pastrone has got all of them because he's in the advisory board of this our center, and this is something that it's it's an international advisory board, and we have got also many international fellows coming from other countries. 2 PhD students are just out from Italy working in our lab. Among the others, it's all together, maybe it's 35 fellows and about 20 plus PhD students, so that this gives some kind of size of it. So, ladies and gentlemen, thank you very much for your attention. I hope that it was just a short presentation only. Thank you.